So this is how to make quartz encapsulated type K thermocouples. They look like this. You got two leads, the junction's in the center. The quartz is there to provide electrical insulation between the two leads so that your molten metal does not ruin it and make a new thermocouple. What?
It wouldn't do that.
It would.
No, it would.
It would.
I've tried.
Anyways, so you need quartz tube. This is from Quartz Scientific. This is 1 millimeter OD, sorry, 1 millimeter ID, 2 millimeter OD quartz tube. It's the finest that you can buy. It's pretty cheap if you order it from Quartz Scientific. That's what I like to use. And then you need thermocouple wire. So this was drawn down, but initially it was from Omega, and it was 0.032 inches diameter. So what we did is we took that, I forget what gauge that is, it's like 20 gauge, I believe. When we drew it down with the smallest die that we had.
That's not true.
In one pass, I believe this is the smallest die we have. Just get it roughly in about 0.03 inches, that sort of range, and that should work with this 1 millimeter ID quartz tube. So take your quartz. I bought a whole bunch of extra bare thermocouple wire here, so you can take this, draw it down to a size that fits into the fine quartz tube here. And I got a whole bunch of extra 4-foot pieces of this, so plenty of material to make plenty of thermocouples. Take your wire, draw it down, cut it into lengths. For my application,
You can draw it down by hand?
yes, you can draw it down by hand, one pass.
How do you do that?
You just sand the ends of the wire to fit through the die, feed it through the die, grab it with some pliers on the other end, just pull it through.
While holding it in a vise.
While holding it in a vise, that works.
Yep.
And you should be able to do it in one pass. Anyways, take your wire, chop it into, well, for my case, 4-inch length pieces. So I got chromel wire over here. So that is labeled as red, or sorry, LML. That is red, as a standard. And then just to double check, it's magnetic. So all these I cut over here should be, yeah, they're LML. They're magnetic. The chromel is not magnetic. What I like to do is just take all those, mark them with a red Sharpie on one end, just to signify that, hey, this is the LML lead, just so we don't mess them up. And so that when it comes to wiring them up, I don't have to monkey around with figuring out what lead is what and then heating up the thermocouples to confirm. You just know by default. Or you can take a magnet to it if you do forget. So take your two leads, clean them up with alcohol to get all the oils off, especially after drawing them. I'll just do one as an example here. Just make sure they're fairly straight because I have to fit inside the quartz tube without resistance. There's the chromel wire. There's the LML wire, which is marked red. Take our quartz tube. And for me, I was just doing 3-inch sections. So you can break this with your fingers or with a pair of pliers, it doesn't really matter. Pliers kind of gives you a bit cleaner of a break. There we go. It's a bit larger, but you get the idea. And then you can come over to this vise. Custom vise just for this purpose. I just slide one lead in, center it with the quartz, go a little bit past center because when we melt this with the torch, it's gonna go back a little bit. So go a little bit past center, go up to the jig. I'm clamping just the wire on the bottom, so it holds it in place, and then clamp the quartz on the top.
Does it matter which one goes in which side?
No, it doesn't. It's all the same in the end. Place it in the jig. We got the wire being held in the bottom here, the wire only, quartz tube up here. Take your other component, straighten it out. I just do this by hand. You just have to figure it out. But straighten it out until this just slides in with gravity and it rests right on the junction.
Let me see if I can capture the junction.
So the idea here is we're going to take our torch, we're going to melt the junction. It's going to become liquid, and then we're going to apply a slight downward pressure at the top.
Pick it up a little bit.
At the top here.
Nice.
You see that?
Yep.
Okay. Yeah. The idea is we're going to melt the junction while applying a little bit of pressure, so that when it actually becomes liquid, you will join together and not create a separation, which will happen if you don't apply pressure. So make sure it's nice and straight and slides easy so that you can do that. And then I'll just go ahead and prepare all 5 of these, remaining 5. Okay, good. So, got my setup going. I got 6 thermocouples loaded, ready to go for melting. They all slide really nicely up and down. No friction there, so they're all really nicely straightened. That's what you want. They're all centered, all the junctions a little bit higher than center because again, when we melt it, it's gonna fall down a little bit. Okay. Now, I'm using oxyacetylene torch to melt the junction. The hydrogen torch also works well in the glass lab, but you have to get some special training for that. And you also have to get special training for this, so talk to Russ or Dale on how to use it. But basically, the setup that I'm going with, torch end, not the cutting torch, just the heating torch, I believe. There's no trigger on it. So oxyacetylene, not on all the way, just like a little bit. Okay. So I'm using about 4 to 5 psi of oxyacetylene and about 8 to 10 pounds of oxygen. Somewhere in that ballpark. All right, so just igniting the torch. I don't have a lot of soot burning here. We're good. Now the idea is apply a slight amount of pressure while heating the junction up. As soon as it's molten, just pull away. Like pull the torch away and then release pressure. That way, you do a little bit up and down to slightly anneal the wire since it has been cold work, that helps. Otherwise, it can start to bend when everything gets molten and soft. Now to check these, I'm gonna pop them out of here. They cool down pretty quick. So that one obviously shifted from the center there, which is fine. But all I'm looking for are like really big cracks.
Hold on. Oh, there we
I don't know if you're able to get that at all.
go. No, I can get it. Just give me one second. There we go. Okay.
So I'm just looking for really big cracks, ones that you can actually feel with your fingernail. If there are none of those present, it should be good. Small cracks are fine. You're going to get those with the expansion of the metal in there and the unequal cooling of both components. So I have actually used one that was completely cracked all the way through and it worked fine. Just as long as the liquid iron or aluminum or whatever you're using doesn't bridge these two dissimilar junctions. It does matter.
It doesn't matter.
So that's a good thermocouple. And I'd also just tug on it.
Where'd you put it? Oh.
Right here. Just tug on it, make sure it's not going to fall apart. It's also a really good one. Also just check for like pits at the junction, or if you see green spots like chromium oxide, it might be bad. Or if there's a lot of black, like an oxide buildup at the junction, it might be bad as well. So those ones I usually just discard and break the quartz, snip the ends off the wire, and then just repeat the process. See, they are a little bent. If you don't kind of like anneal them with the torch a little bit beforehand, all the residual stress from it not being so straight kind of bends the quartz as it gets soft with the torch. So kind of annealing, doing a little bit of an anneal pass really helps with that. That one's good too. So 100% success rate there. Usually it's not as good. Usually you'll get one or two that fail. It's just a matter of tweaking your method of melting the junction. I found that only apply heat until it's molten and then quickly release. The longer you hold it and try to make the junction bigger, it just seems to crack the quartz more often, and then in some cases it might form like pores in there. So less heat seems to be better, and then just doing a anneal pass to remove any residual stresses so it doesn't bend as much when you're making them. This should be it. It's a very simple tutorial on how to place the thermocouples. So say I don't have a bigger mold to simulate this on, unfortunately, so I'm going to use 2 pouring cups. Say this is my mold cavity, my 2 halves of the mold, and they go together like this. Say that's perfectly aligned. And I want the thermocouple to be in this area here, just to collect the cooling rate of this giant section. So what I was doing, take a really long, I got a 2 millimeter drill bit here. Go to one side of it, or one half of the mold. Say I want it right center, so you can get very precise with this. I'm not going to be precise. Drill it. Okay, I got my hole all the way through. Line these back up. Again, this is a huge mold cavity, but like I had 8 millimeter bars, so it was a lot finer. But then you can line it up, use that hole that you just drilled as an alignment hole. Drill all the way through. I got the 2 halves. And I take a really large drill bit to counterbore. This is my depth gauge. Obviously, it's not going to be the same on this. Drill a little bit farther in your mold since you're going to have more material to work with. And this just allows you to pack in between the quartz and the mold itself so it doesn't leak out. So there we got our 2 halves. Align them again. Take your thermocouple, feed it through. First, I would do this. I would take it, center it with the parting line, since I want it to be in the very center. Center the junction with the parting line, then just take over here. Kind of takes a little practice. Get right where you want to bend a 90-degree angle in it, like that. And I would do another 90 upwards to facilitate twisting the junction together. And then you can take that and feed it through. So there, we got it fed through. There. Yeah, so now you know when that's all the way against that surface, you're right at the center. And I would just take my pliers again and bend the other side. I'm going to have some fine needle nose to do this. Bend another 90, and another 90. That was a horrible 90. But anyways, so now it's centered and it can't move back and forth. So that thermocouple's in there. And then what you can do, take some fresh Kanban sand and just pack all the way around the quartz tube and the mold surface. I just made up a nail, I ground it down a little bit, that would fit, and I would just pack sand all the way around so that you get a really good compacted sand. And that seemed to work best. Just using Kanban sand, no core paste or anything like that. So once that's cured, then you can wire it up. For that, just made a whole bunch of these extension wires. So you got connector on one end, and then just bare wires on the other. And you just take red to red, since I already marked that, and just try to twist them together the best you can, which I'd usually use a couple pairs of needle nose, which I don't have out right now, but just twist them together, get a really good junction, make sure it's nice and tight. This one's a bad one, but just as an example, say that's good enough. And then when all's said and done, just snip that junction off, and then you're good to reuse that extension wire. Yep, that one goes over there. And that's it. Easy. So I just wanted to show an example of how I was using these thermocouples. So I was casting gray iron into bars of different size diameters, so ranging from 8 millimeters up to 30 millimeters, just to just to collect cooling rate data and compare that to the microstructural effects. So you can see right here we got the 8mm bar cools down quite fast, and the 30mm bar over here in blue cools down a lot slower. And you can very clearly see the eutectic reaction, where that occurs over here, and then the eutectoid down here. So you can see these thermocouples work quite well, and you can get some really nice cooling data with them.